So model significant. So we can conclude that there is a correlation between the number of times you go out to eat and the amount of money that you spend on food. And it's always per week. Okay. How did we come to this conclusion last time? Last couple of times.
Confidence interval on beta 1.
Okay, first step we did we found a confidence interval on beta 1, and if it contains 0, then model is not significant. Doesn't contain 0, model is significant. What is the second approach?
T-test.
A t-test. Specifically t-test for beta 1. Those are the previous approaches that we used. And last time we did ANOVA. And I mentioned ANOVA serves a specific purpose, even though we can come to this conclusion about model significance using these two procedures. We need ANOVA for a different reason. What is that? Why can I not simply rely on these? Well, if data is given, cannot use regression. We have to go to non-parameter. Just if you have more than one control variable, more than one, or is it more than two? More than one. Okay. Do we agree with that? Not a control variable. You mean X, the predictor. Yeah. Okay. More than one. Huh?
Two. You already have
More than two. Now, could I use for two? Absolutely, I agree. You can use an ANOVA in this case. Also, that's exactly what we're about to do. But more than two is what we do in practice, because there is the concept of family-wise error control. Your conclusion is more likely to be incorrect if you keep on doing individual t-tests for every single pair that you can think of. We don't want that. We don't want to make the wrong conclusion. So when it comes to simple linear regression, in other words, you have a response, one predictor, these two would suffice. You can use an ANOVA. We're about to do that. But when it comes to multiple linear regression, chapter 3, ANOVA is the only way. Good. So from last time, what is the degrees of freedom for regression? One. What is the total that we have? Total number of observations. For this example, was it 5 or 6? 5. So here I must have n minus 1. So 4. Which would mean there I would have. So another way to look at it, this would be the number of predictors that you have, which is 1. And that would be n find is the total number of parameters that you have. 5 minus 2, you get 3. Add them together, you get n minus 1. We did find MSE last time, so let's go back and find what that number is. Well, we are going to sort of go backwards to find MSE. Last time we had MSE to be 9.6, so whatever it is that, we'll give you the estimate for sigma. SSR, sum of squares for regression, sum of squares for error. Last time I split the total variability in the data. Yes, then I split it off as that. So brief. What is that? yi minus yi hat. Residual or residual error. Sum of squares, residuals would go right there. Since we know MSE, we calculated a verdict. Let's not do it again. So MSE is 9.6. If MSE is 9.6, what is SSE? SSE is obtained, well, MSE is obtained by dividing SSE by, is it n minus 4? Is it n minus 2? It's n minus 2. So I can multiply 9.6 by n minus 2 to get SSE 9.6 times 3, 28.8. Good. We want to find SS. Oh, there are a couple of ways to do this. Sure, I can do that. Take each fitted value, subtract the mean from it, square it, sum all of them together. But there is also an easy way. Did the homework, you'll know. I'll give you a hint. It has to do with that. Variance, specifically variance of what, Dennis?
Y.
Y. So that is proportional to the variance of Y. And we know we can find the variance easily using a calculator. Yes, we have the data for Y, which I'm missing, but you have it. So if I use the calculator, I know that variance of Y is simply 1 over n minus 1 times that. Yes. In other words, it is simply SST divided by n minus 1. 0. So if you take SST, which is right here, divide by n minus 1, you get the variance of Y. So use your calculator to find the variance of Y. I believe we did this already. So you can just look through your notebook. We have X values 1, 2, 3, 4, 5, Y values in this table. How do we find the variance?
And then go over to count.
This
And
count
then one var stats.
and What do we select? First list is X, second list is 1. So second 2, list 2, enter. Mean sum of the y values, sum of squared y values. Sx is simply the standard deviation. We don't want the standard deviation. We want variance. So what should we do? Square it. So I'm going to round it as 17.6. I end up getting 309.76 for the variance. You can tell me what the total sum of squares is. So I multiply the variance by n minus 1. I'll end up getting s is 3 minus 3. So the reason why I'm doing it this way is because you don't have to do that part by typing it. It's too much work. The calculator gives you the variance. So if you know this relationship, you can easily find SST. Good. So SST $1239.04. SST is 1239.04. What is SSR? 1210.24. How did you get that, Jim?
Subtracted SST minus SST.
So all you have to do is subtract or move SSR to, SSE to the other side. You'll get this. So 1210. Add those two, you will get 1239.04. What is MSR? The mean squared corresponding to regression. The same. Why is that? Divide by 1. Take this value, divide, you get that. We just did it backwards because we knew MSE already. Take that value, divide by df, you would get that. Don't add these two. Can't add averages and say, oh, that is the total mean. So you can't add those two. From last class, what is F? Huh? Good. MSR divided by MSE. So you divide those two. So 1210.24 divided by 9.6, which is
126.067.
126.067. I'll write it as 0.07. Based on what I ended with last time, I drew the F distribution. Do you expect to reject the norm? Norm being model is not significant. Alternative model is significant. Do you expect to reject the null?
Yes.
Yes. Why?
It's a stupidly high F statistic.
Very good. So as the density. That's an F distribution. Typically, a number that large would simply imply you're rejecting the null. Because F would get closer to zero pretty fast. What is that shaded area called? Rejection region. What would that shaded area correspond to?
Alpha.
And that is simply the level of significance or the probability of type 1 error of positive rate. In other words, if I rejected the null, the chances that I could go wrong has to be alpha or below. Typical value, 0.05. So I want that error to be 0.05 or below. And we use that to find the critical value. Let's decide on a table first. That tells you exactly what you should do. Alpha is the area in the right hand, right hand. And it's a good thing I didn't write it here. If you use that table, this is alpha. You can go and Google. You might find another table which would use 1 minus alpha below it. So we have DF1. What is DF1?
Degrees of freedom of MSR.
MSR, and that value is
1.
1. So I'm going to stick with column 1. DF2 is 3. So column 1, block 3, and within that block corresponding to DF2 of 3, we have 4 options, 4 significant levels. Of the 4, which one should we pick? 4 values, 5.54, 10.3, 17.44, 34.12.
With our current alpha, we would pick 10.3.
10.3.
We could pick any of them and still reject.
That is true. Because F is pretty large. That's what I was talking about earlier, that things would become smaller rapidly. Starts with 4,000 something over here and drops down to 98, 34, 21.2, and so on. But here, all we need is that 10.13. If the critical value of 10.13 is right there, and the test statistic is 126.07. So maybe over here. Yes,
Do you want the p-value?
patience. We're together. So it's right over here. Should we reject the null? Yes. So our conclusion is to reject the null. If I reject the null, the model is significant, which is something that we've seen before with the other 2 procedures. In practice, one typically would not go for the critical value method, use it, but often the it's used for educational purposes. P-value is what people usually go with. What is p-value? Do we remember? I don't want the number, I want the definition. So if we went and collected another sample, what are the chances that I will see something just as extreme or more extreme under the null? So it is going to be very, very small. So what we are trying to suggest is this did not happen purely in a random sense. There is some underlying effect, right? So that's the formal interpretation. We'll stick with the informal one. It's easier to follow. I think that's the best way, in my opinion. P-value is nothing but an estimate of alpha in a sense. So that is simply the probability of you going wrong under the null and based on the current data that you have. What are the chances that you're wrong in rejecting the null and coming to the conclusion that the model is significant based on current data? That is the key word. If the data changes, perhaps you may get a different conclusion. Well, do we expect it to be significantly large? No. As I said, probably over here somewhere, that is our test district, and that is 126.07. And I just mentioned that sort of is an estimate for alpha. What is alpha? Area above the critical value. When it comes to p-value, you are using the data, so it will be the area above the test distance. Yes? Well, if that curve is just getting closer and closer to zero, and you're looking at the area above the test distance, that will be very, very small. Yes? So I'm expecting a number close to zero. This part can be done using a calculator. So we want to find the p-value using an F distribution. That is simply the area above the test statistic. So button right next to clear bars, that's what we use to find TCDF. So second bars, to give you all distributions. If you scroll down, number 10 is FCDF. We want to find the area above the test statistic. So the lower endpoint must be the test statistic, which is 126.07. The upper endpoint has to be E99. What does E99 correspond to, Governor?
10 to the 99th power.
Infinity. Or an approximation of infinity. DF1, DF2. DF1 is 1, DF2 is 3, and I get 0.0015. The newer version of the calculators perhaps has it as lower upper DF1, DF2. Is it calculator paste?
It's paste.
Paste. 0.00 Chances, the problem, I set an alpha of 0.25. In other words, if I rejected the null and concluded that the model is significant, the chances that I'm wrong has to be 5% or below. So I collected the data, I looked at the data. The data is telling me, well, based on everything, if you rejected the null, the chances that you would be wrong is 15 in 10,000. Yes. Would we consider that to be small? Yeah. Is it smaller than what I said at the very beginning? Yes. So you reject the null comfortably. I would never put p-value to be exactly 0. It is sort of as wrong or goes against the principle of statistics if you set p-value to 0.1.
It would be impossible to reject the null.
It would be impossible to reject the null, but that is not true because we are doing this based on the evidence that we see. It could change, it may not change today, maybe tomorrow, it could change. Then you may always ask me, well, if that's the case, if data keeps on changing and your conclusion keeps on changing, what is the point of doing it at all? Yes, the underlying principle here is if you have a consistent effect, no matter how many times you try, you would consistently get the same answer, or you would reach the same conclusion. Going back to this, if you repeat it based on the data that we see, if you repeat it the process 10,000 times, 10,000 different samples, the number of times you would disagree with this conclusion or go against the conclusion and conclude that the model is insignificant will be how many? If I did it 10,000 times, 10,000 different samples, 15. So 15 times, I'm going to get a different conclusion. Still, that implies consistency. Do you agree?